Hello, my name is Shawn Ogunseye. I am an incoming assistant professor of computer information systems at Bentley. The paper I will be discussing with you was co-authored with Jeffrey Parsons of Memorial University and Roman Lukayenka of HEC Montreal, and is titled "To Train or Not to Train: How Training Affects the Diversity of Crowdsourced Data." Organizations used to be limited to their employees to perform business functions. However, as computing technology has become more pervasive, organizations can now leverage large pools of external workers through crowdsourcing. Howe in 2006 defined crowdsourcing as taking a function once performed by employees and outsourcing it to an undefined network of people in the form of an open call. Many tasks can be outsourced to the crowd, but we look specifically at what my co-authors have termed observational crowdsourcing. That is, engaging people to provide data based on their experiences and observations. An underlying challenge of sourcing information from an unknown crowd is the risk of collecting low-quality data. But organizations mitigate this risk by training their crowd, assuming that increasing the knowledge of data contributors will positively affect data quality. However, organizations may have new requirements for their data at any stage in a data-driven decision-making process. Organizations will therefore be better off if they understood how training affects the capacity of data to adapt to unanticipated requirements. For example, Yelp data, which was collected to help customers evaluate the services businesses provide, has been used to track the outbreak of foodborne diseases, estimate probability of health code violation in restaurants, and to predict the continued success of businesses. When crowdsourced data cannot meet new business requirements, organizations expend additional resources repeating the data collection process or redesigning data collection systems. And they may permanently lose information if the phenomenon of interest is transient. We refer to this act of using data for purposes different from their original purpose as data repurposing. Data repurposing is a bedrock of data analytics. Before machine learning algorithms are applied to data, businesses must collect, store, and prepare raw data for analysis based on business requirements. And as business requirements change, data are repurposed to meet these new requirements. But for data to be repurposable, they must be of high quality and must be diverse. That is, they must contain information about the different features of an observed phenomenon. Using the theory of selective attention as our overarching theory, we predict that in observational crowdsourcing tasks, trained contributors will mainly focus on the attributes of target entities that are necessary to identify them and will report fewer non-diagnostic attributes of these entities and fewer secondary entities. Training will therefore adversely affect data diversity and data repurposability. In order to test this prediction, we carried out a simulated observational crowdsourcing experiment where participants were required to report the sighting of any two artificial insects called tyrant and non-tyrant. The experiment was designed to be similar to Pokemon Go. We randomly assigned 84 participants into 3 groups: an explicitly trained group, an implicitly trained group, and an untrained group. We presented each group with 20 images, 16 containing artificial insects, and 4 images were used to screen out participants who did not pay attention during the task. We told trained participants that tyrants are harmful to their characters in this hypothetical game, and non-tyrants will provide extra energy to their characters. The explicitly trained group was taught the rules to identify a tyrant and shown examples of tyrants. We taught them that tyrants have a short tail, light blue body, 2 or 3 buttons on their body, blue wings, 1 or 2 rings on each wing. The implicitly trained group learned only from exemplars, while the untrained group served as the control group. Some of the artificial insects presented in the actual test had attributes that differed from the insects presented during training. For example, this insect has a two-lobed antenna and this insect has a light blue tail. Some images presented in the task also contain secondary entities that are everyday animate or inanimate objects like butterflies or chain link fences. Participants were shown each image for 40 seconds and asked, "What do you see?" We expected explicitly trained contributors to show more selective attention than implicitly trained contributors because they have learned the inclusion rule and know which attributes are diagnostic, unlike implicitly trained contributors who had to study several exemplars to determine which attributes are diagnostic. We predicted that untrained contributors who will show the least selective attention will report more diverse data than trained contributors. We also predicted that explicitly trained contributors will report the least diverse data as they will show the most selective attention. Additionally, we were interested in the effect of training on the capacity of contributors to report attributes they had not encountered before. Based on selective attention, we expected implicitly trained contributors to report more attribute variations than explicitly trained contributors because they have attended to more of the entity's attributes to identify diagnostic attributes and are more likely to notice if these attributes change. We also expected implicitly trained contributors to report more attribute variations than untrained contributors because for the untrained contributor, every attribute is new. There are no fixed attributes which we to compare other attributes, and no attribute is more significant than another. Nonetheless, we expected untrained contributors will report more variations than explicitly trained contributors because we expected explicitly trained contributors to ignore variations that involve non-diagnostic attributes. And since the justification for training crowds is that training improves information quality, we compared the ability of the groups to report diagnostic attributes that can be used to identify the entity. We also compared the ability of the trained groups to classify the insect either as a tyrant or non-tyrant. We expected the untrained group to be incapable of this level of classification. For information diversity, untrained contributors reported more diverse data than trained contributors, while implicitly trained contributors reported more diverse data than explicitly trained contributors. Untrained contributors and explicitly trained contributors reported similar amounts of attribute variation. And for information quality, we found that there was no significant difference in the ability of trained and untrained contributors to report diagnostic attributes. Nonetheless, trained contributors were better at classifying entities. The implications of our findings are as follows. When crowdsourced data may be repurposed, untrained contributors should be preferred to trained contributors. And for long-term projects, recruitment should be ongoing. New contributors who are less affected by selective attention should be recruited into crowds to refresh the crowd. And for attribute variations, when implicit training is not possible, organizations will be better off using untrained contributors than explicitly trained contributors. And finally, untrained contributors can provide accurate data at the attribute level, but will result in additional costs to classify the data. It has been my pleasure presenting to you. Thank you.